Okay, in this video we're talking about heat capacity. We're talking about within that thermal energy, what that is, what temperature is, because thermal energy and temperature are a little bit different, and what the specific heat capacity is for something, and basically how energy relates with all of this. So let's kick off with thermal energy. Now, when we consider matter as a whole series of particles, this is just a substance with particles in a regular array. That means they're all in a nice regular pattern. Those particles are vibrating backwards and forwards. We might represent that by sort of drawing little shake lines, if you like, to show how they're shaking. Now, the more that they shake, the more energy they have. Okay, so and we would call this moving energy kinetic energy. So kinetic energy of particles. Okay, so the more they shake, the more energy they have, and the more temperature, the more thermal energy. We're going to get a little bit tricky here. It's easiest just to contrast thermal energy and temperature, but I'll finish this and then we'll go from the general to the specific. So generally speaking, the kinetic energy of the particles is the temperature. Okay, so that's not strictly speaking correct, but it's close enough for now. So as something gets hotter, that leads to more movement of the particles. Okay, so that's really important. That's the key idea upon which most of this is built. Now we get to this idea of thermal energy. So thermal energy is the total amount of energy. So think thermal energy, think total E, in a sample. Okay, so we might have 10 atoms, this is just for example, but they have say 50 joules of energy each. This is totally random, I have no idea. That sounds like a hang of a lot of energy for 10 tiny little atoms, but that means our total amount of energy would be 500 joules. Just for, if let's write that in atoms. Okay, so that 500 joules is our total energy, which is our thermal energy. Now, if we look at the temperature, the temp is the average energy per molecule or atom, so in this case 50 joules is our average temperature. However, we don't represent that in terms of joules. We would maybe write 20 degrees centigrade, Celsius. Okay, so and we use this scale to represent the temperature. Now, just an example to bring that all home. If we have if we consider this exam question from last year, we have a swimming pool with lots of water in it, and we have a barbecue hot plate. Okay, this is my Bunsen burner, if you like. Okay, so barbecue hot plate here, and we've got the pool. Now, this one can get up to 300 degrees Celsius, for instance, but the pool is sitting at 20 degrees Celsius at just air temperature on a nice summer's day, maybe summer's morning. The pool, hang on, I'll pose it as a question. Which one has the higher thermal energy, and which one has the higher temperature? Okay, and the answer is that the pool will have the higher thermal energy because that is the total amount of energy. All of those molecules, there's probably thousands of times the number of molecules at 20 degrees Celsius each. You add all of that energy up, it's going to be more than the at least 1,000 times less molecules in the hot plate, which even though they're at about 15 times the temperature. So 15 times the temperature is nothing compared to 1,000 times the molecules when there's, you get the idea. So thermal energy is different from the actual temperature. That's what I was getting at. Now the last part I want to look at is this idea of specific heat capacity. the specific heat capacity, and this is a measure of the amount. So you have a symbol C, not to be confused with the speed of light, and this is the amount of energy required to raise a sample, let's say 1 kilogram, because that's a standard measurement, to raise 1 kilogram by 1 degree Celsius. So we want to increase the temperature of a 1 kilogram block of aluminium by 1 degree Celsius. We'll have to put in a certain amount of energy to do that, and that's what this heat capacity, or specific heat capacity, is. Now, I'm not sure why it's called specific heat capacity, but I think it's to do with when you compare it to the phase changes, and you have further energy that's used in the situation. But this is the specific heat capacity. If we were to draw a graph, of the I'm not sure how energy required and temperature. As the temperature is increasing, this is a very simple graph, and I'm not considering any phase changes, so no changes from solid to liquid or liquid to gas, or the reverse. As the temperature increases, so going this way, as temperature increases, the amount of energy required or stored in that substance, in the movement of the particles, that energy is increasing. Okay, there's a formula to represent this, and for some reason they use Q as the energy, and that amount of energy stored is dependent on a number of things. One of them is that specific heat capacity. One of them is the temperature that you're raising it by, T. We actually call it delta T with a triangle, because a triangle means change. And it also depends on the mass. So if you've got twice as much mass, it will take twice as much energy to raise it by a particular temperature. So here's this formula. The energy is the mass of what you're trying to raise times the heat capacity of that substance times by the change in the temperature. So this is an important equation. You need to know exactly what each of these things are and what their units are. So Q is measuring energy, so it's measured in joules. M is mass, measured in kilograms, because that's the SI unit for kilograms. Even though it's got that K in the front, kilograms is the SI unit. Not sure exactly why it worked out that way, but it is. The heat capacity is, the units are made up to balance all of the other units. So I'll get to that shortly. T is the temperature, and that's in degrees Celsius. And it's a temperature change, so it could actually be in, you don't say degrees Kelvin, but it could be in Kelvin as well. Kelvin is the same scale, same divisions on the scale as degrees Celsius. It just has a lower 0 point, starts at absolute zero in theory. Okay, so how will we work out the units of that specific heat capacity, C? I will show you. I will show you just because, and then we'll finish up there. We would look at, it's another colour, purple. We would rearrange the equation to make C the subject, that is to bring C out the front. So to do that, we're going to have to divide Q by M and by the change in temperature. And then we just have to make a parallel kind of units equation. So the units for C will be equal to the units for Q over the units for M over the units for change in time. So overall this is going to be joules per kilogram per degrees Celsius. So we could also write that as joules per kilogram with a -1 per degrees Celsius, -1 as well. Okay, and that pretty much covers it. Go back and watch the video to get all the finer points, and maybe try some past exams with these questions to get used to them. Next video is going to be on phase changes and how energy works when you change the phase, because there's another little formula which relates to it. I should say as well that this formula has meaning. It's not just a formula for no reason. You have to understand the concepts behind it, and you'll be able to use it very well once you understand the concepts behind it. Start with energy. Think energy, and you'll be right.